Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss row operations. So in this topic, we are going to review the row operations of a matrix. We will see that each row operation is actually a linear operation and thus can be represented by a square matrix. We will find these matrices and we will observe that these matrices are indeed invertible, for the operations themselves are invertible, and consequently we will find the inverse of each of these row operations. Now, recall that there were three row operations we introduced. However, in Gaussian elimination, we only used the first two. So the operations were swapping two rows of a matrix, adding a multiple of one row of a matrix onto another, and multiplying a row by a non-zero scalar. Now previously, we represented these operations by an italicized capital R with an appropriate subscript. There was a very good reason for doing this. Recall that all linear maps are represented by such italicized capital letters. Consequently, this was meant to foreshadow the fact that we can actually represent each of these row operations by a linear operator, that is, an M by M matrix. Now, suppose that we have a linear map mapping Rn to Rm. So A is representable by an M by N matrix. Suppose we'd like to swap two rows of this matrix. Now recall that matrix-matrix multiplication can be found by multiplying each column vector of A by the matrix B. So if A has the column vectors A1 through AN, then B times A is B times each of these columns or vectors. Now, how can we swap two entries in each column vector A sub k? Because if we swap entries I and j in each column vector and we apply that to all columns, then we have essentially swapped rows I and j. Now, first of all, we have to realize that swapping two entries in a vector is a linear operation. Why is that? Well, it really doesn't matter. If I have two vectors u1 and u2 in Rm, and if I calculate a linear combination of those two and then swap entries I and j, that's not going to be any different than swapping those two entries in u1 and u2 separately and then taking that same linear combination. So we're guaranteed that swapping two rows is a linear operation. Also, the resulting vector will be m-dimensional, so we require a linear operator. Thus, this linear operator is going to be an M by M matrix, as all of the column vectors of A are m-dimensional. Question: what is the matrix that swaps rows I and row j? Well, interestingly enough, in order to swap rows I and j of a matrix, all we have to do is take the identity matrix and in that matrix swap rows I and j. So now, where there used to be a 1 on the diagonal, we have a 0, and now we have 1s in locations ij and ji. Now, suppose we have this 5 by 3 matrix and we would like to swap rows 2 and 5. For it seems as if we are currently performing Gaussian elimination. We've eliminated everything under the leading non-zero term in the first column, and now we are swapping rows 2 and 5 to place the largest entry in absolute value at that location. So to achieve this, we can multiply on the left by the 5 by 5 matrix that swaps rows 2 and 5. That's this matrix here, which is the identity matrix with rows 2 and 5 swapped. So if we now multiply these two matrices together, we get the matrix that we started with, but now with rows 2 and 5 swapped. Now, how do we undo the operation of swapping two rows? Well, interestingly enough, we undo that operation by swapping those two rows again. So what that means is that this particular linear operator is its own inverse. So to undo the swapping of two rows, we simply have to swap those two rows again. What that means is that if I multiply the matrix that swaps two rows by itself, I get the identity matrix. You can see that here. If you take these two matrices, which swap rows 2 and 5, you will then see that the result is the 5 by 5 identity matrix. Again, let A be a linear map mapping Rn to Rm, and this is being represented by an m by n matrix. How can we add a multiple of one row of this matrix onto another? Again, we have that B times A is simply B multiplied by each of the column vectors of the matrix of A. So the question is, how do we add a multiple of one row onto another? Well, we need a matrix B that adds one entry of each vector, or a scalar multiple of one entry to another for each of those vectors. So if we perform the same operation on each of the column vectors from A1 through AN, that will have the effect of adding a multiple of one row onto another. Now, adding a multiple of one entry of a vector onto another is a linear operation. Why is that? Well, if you think about it, if we have two m-dimensional vectors, u1 and u2, and we take a linear combination of the two, and then add a multiple of one entry onto another, you'd get the exact same result if you first added, again, that multiple of one entry onto the other in both u1 and u2, and then took the same linear combination of the two results. Thus, such a mapping would be linear. Also, the resulting vector must still be m-dimensional, and so therefore this operation must be representable by an m by m matrix, so a linear operator. So the question is, what is the matrix that adds alpha times row I onto row j? So once again, to determine the matrix, let's take a look at the identity matrix. Well, this just maps the vector u onto the vector u. But when it comes to calculating the jth entry of u, what we want to do is we want to add to u sub j alpha times the entry u sub I. What that means is we have to set that one entry there to alpha. So that one entry there will then, when we are calculating the jth entry of the product, that will be alpha times ui plus uj. So again, adding alpha times the ith entry plus the jth entry, and that will end up being the jth entry of the result. Now, we're performing Gaussian elimination here, and we want to add 0.5 times row 2 onto row 3. So in order to achieve this, we multiply on the left by the matrix that performs this operation, which is this matrix here. So if you now multiply the matrix on the right by this matrix on the left, you get the result of having added 0.5 times row 2 onto row 3. Now, can we undo the operation of adding a multiple of one row onto another? Actually, yes, we can. Just subtract that same multiple of the one row from the other. So if we have the row operation of adding alpha times row I onto row j, the inverse of that operation is simply adding negative alpha times row I onto row j. And either way, in whichever order you perform this in, if you do one and then the other, you will end up with the identity matrix. So, for example, from the previous page, we added 0.5 times row 2 onto row 3. To undo that, we add negative 0.5 times row 2 onto row 3. And if you perform matrix-matrix multiplication on these two matrices, you will see that you do get the identity matrix. Again, let A be a linear map from Rn to Rm, and thus it may be represented by an m by n matrix. How can we multiply a row by a non-zero scalar? Well, once again, if we multiply A by B, that is equivalent to multiplying each of the columns of A by the matrix B. So how do we multiply a row by a non-zero scalar? What we need is a matrix that multiplies an entry of the vector by that non-zero scalar. Now, the process of multiplying an entry by a non-zero scalar is going to be linear. For after all, it doesn't matter whether or not we calculate a linear combination of two vectors that are m-dimensional and then multiply one of the entries by a non-zero scalar, or we can multiply the corresponding entry by that non-zero scalar in both u1 and u2, and then take the same linear combination of the two results. Those two will be equal. Also, the resulting vector must still be m-dimensional. Thus, this operation must also be representable by an m by m matrix and is thus a linear operator. Question: what is the matrix that multiplies the ith row by a non-zero scalar alpha? Well, once again, we have here the identity matrix. However, if we wanted to multiply the ith entry of the vector by alpha, assumed to be non-zero, consequently, when we get to calculating the ith entry, which is by multiplying element-wise the ith row of this matrix by the vector, that means we need to change that entry on the diagonal to alpha. So suppose, for example, we wanted to multiply row 2 of this matrix by negative 0.125. Essentially, we are making the leading non-zero entry of row 2 to be 1. Well, in that case, we multiply on the left by the row operation matrix that multiplies row 2 by negative 0.125, which is this matrix here. And if you are now going to multiply these two matrices together, you would get the following matrix we see here. Now, can we undo the operation of multiplying a row by a non-zero scalar? Well, it's important that it's a non-zero scalar because if it is non-zero, yes, we can. All we have to do is multiply that same row by the multiplicative inverse of that scalar. Consequently, the inverse operation of multiplying row I by alpha is multiplying row I by the multiplicative inverse of alpha. And whichever order you multiply these two matrices in, you get the identity matrix. For example, here's the matrix from the previous problem. If I multiply it by 1 over, which is negative 8, multiplying those two matrices together gives you the identity matrix. Following this topic, you now know that each row operation can be represented by a square matrix. You also understand that each of these matrices has inverses, and you know what these inverses are. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!